functions. This is in your summer packet, so this is kind of a little repeat here. But then we're going to get into the IVT, and the IVT was also in your summer packet, but we're going to do some different stuff with it. We're going to take it a little bit further. And then I think beyond that, we'll be into like some relatively new stuff for you guys. So these classic functions, I put this section in here just simply so that when you see a certain type of function, you can be like, oh, that's going to be continuous everywhere, or there's these potential issues with continuity, just so you can kind of have some general categories. So hopefully this will save you some time. That's kind of what I'm trying to say. So a polynomial function, what is an example or examples of a polynomial function? There you go. So she said x squared plus 3x minus 5 or something like that. What kind of a polynomial is that? It's quadratic. What's another example of a polynomial? There's quadratics. And x cubed, what do we call that? A cubic. And then what's the next degree up? To the fourth power, and we call it a... No? Quartic? Have you ever heard of a quartic? No. Quartic is a fourth power. What is a first degree polynomial? Linear. Yeah, so lines, parabolas, cubics, quartics, fifth power, sixth power, or whatever those are called. Those are all examples of polynomials. Does that make sense? So these are always continuous for all x. All continuous. So if you see a polynomial, you know it's always continuous. It's a good thing. Makes it a little bit easier. Rational. What kind of bad things could happen? When I say bad, I mean points of discontinuity. What kind of things could happen with a rational?
0 in the denominator.
Yeah, 0 in the denominator. And what could that 0 in the denominator cause?
Hole.
Could cause a hole or a removable discontinuity. What else? Yeah, vertical asymptote. So with rational functions, you have potential discontinuities. Potential, not guaranteed, but potential all over the place. You could have holes, vertical asymptotes, things like that. Radical functions, when I say radical, I'm talking about like y equals root x, that sort of thing, sort of x. What kind of issues with continuity could come up if you have a square root function like that? Imaginary numbers, right? Yeah, so we're graphing on the real number plane, the x and the y axis, then this won't work. And so we're going to look for negative inputs, leading, of course, to imaginary numbers, that kind of thing. So there could be whole long stretches of the domain that are not part of this. I should say whole long stretches of the x-axis that are not part of the domain, simply because you can't do the square root of a negative and keep it real, right? And then what about trigonometric? Of the normal 6 trig functions, there are 2 that are continuous everywhere. You guys know what those are?
Sine and cosine.
Yep, sine and cosine, always continuous. And then the other 4, tangent, cotangent, secant, and cosecant, the other 4 have what kind of discontinuities that show up? That's right. So secant, cosecant, tangent, and cotangent. These are all going to have vertical asymptotes regularly, right? Periodically, they're going to have these vertical asymptotes. And so, I like I said, the only reason for me showing you this or even talking about this is just so you have a general concept of, hey, it's a rational function. There could be very realistically some points of discontinuity that I got to deal with. Polynomial, you're free to assume that it's always continuous. So just keep those in mind, just to hopefully it. Okay, so we're going to look at the intermediate value theorem, and this is where we will likely finish today. The IVT has kind of the very rigorous, precise definition that you see there at the top. I'll read it briefly. It says, if f is continuous, and it's bolded and underlined, that is the condition for the IVT, the intermediate value theorem. You can use IVT as an acronym for it, and that's pretty accepted, I think. So if you do have a continuous function on the interval from a to b, and f of a doesn't equal f of b, k is some number between f of a and f of b, and there's somewhere on that x interval, we'll call it c, where f of c, the y value, equals whatever that original y value was. And this is a really confusing thing to read, right? There's f of c's and k's and a's and b's and f of a and f of b, and I mean, it's really easy to look at it and just be like, what? Let's boil it down to this. informally, this is saying that if the y value of a function passes from one y value to a different one, you got to hit all the y values in between. So I think a graph is a kind of a nice way to look at this, and I'll just sketch in a little tiny graph up here. So if you've got your y-axis and you've got your x-axis, here's A, here's B, and say f of A is up there somewhere, and f of B is down there. Does that make sense? Well, maybe like right there. So there's f of A and f of B. The red dot is f of A. The blue dot is f of B. Here's the whole point. Do you guys see the range created right here? I just highlighted in red. Isn't that the range for the y values? If f is really continuous, don't I have to hit all of the y values within that little red range? There is absolutely no way for you to connect those two dots, the red one and the blue one, without hitting all these y values in between. You can't do it. So if you could like try to circle around, but just hit them all, didn't I? That doesn't work. Obviously there I hit all of the y values in between. Can you see that? So this red range, in fact, we could continue this red range all the way over through here, you know. So there's no way to connect them. I mean, I could go up and down and try to avoid it, but eventually I got to go back down there. The only way you can avoid that red range of numbers is if the function you're dealing with is not continuous. Yeah, so if you had a jump, so if you did this and then this, we just avoided the whole red range, didn't we? Totally skipped over it. But remember, the condition for the mean value theorem is that f must be continuous. And if you've got a discontinuous function like this, the IVT doesn't even apply. Did I say mean value theorem? Later on, there's going to be mean value theorem, and I feel like maybe I just mixed that up. We're talking about the intermediate value theorem. Sorry if I did. You know, the video will tell the truth. You could always go back and watch it and be like, you totally did say that. Anyways, so if this is continuous, then I'm going to hit all those numbers in between, and possibly multiple times, right? The only thing we can guarantee is that if f is continuous, then I'll be hitting all those y values at least once. At least once. Possibly 2, 3, 4, 5, but at least once. Okay. Conceptually, does that make sense? The picture probably helps a lot. Isn't the picture like, you know, the phrase, a picture's worth 1,000 words? And you look at the picture and it's almost like, whoa, why was that so hard to get? But then when you look at the words, you're like, what? Right? It's pretty scary. So I hope the picture helps. So why don't we take a look at A. A says use the IVT. That's a really key phrase. This is similar to your notes. To prove that that function has a y value of 5 at least one time on 0, 3. And don't forget to write that f of x is continuous. If you're going to try to use the IVT, you better say that. So we'll work on how that would be kind of woven into the explanation. So we're going to kind of do this one together. So I'm wondering if we are trying to prove that this will have a y value of 5 at least one time on the interval 0 to 3. And this is an interval. It's 0 is less than or equal to x, which is less than or equal to 3. Those brackets mean a closed interval. So anyways, any ideas on what you would do? I'm just looking for a strategy, something that would kind of get us started off on the right foot. Nick, what do you think? Plug 5 in for what? Okay, so I could, but then that would not be using the IVT.
Do plug in 0 times, right?
Does that make sense, Nick? I think your strategy could work, except it said use the IVT. Okay?
Do you
Sorry.
plug in like x for 0, 1, 2, 3, and then say they have 5?
And so let's see here. So that I kind of partially like your strategy. And I'm assuming that you said 0, 1, 2, 3 because the interval is from 0 to 3. Okay. So what I'm not going to do, and I don't know how, let's do this real quick. I don't think we're going to get the thing you said. Let's see here, it'd be, nope, 1. So I think, let's try this really quick. So as Zoe said, she said, let's try 0, 1, 2, 3 and see if we get an output of 5. So technically that wouldn't really be using the IVT. But you know what we can do is we can use some of that data that you suggested to kind of help us narrow it down. Let's figure this out really quick, and then I'll come back to you, Anna. You can maybe help us do what we need to do with this information. So let's do this real quick. She said plug in a 0. So if I plug in a 0, what do I get? 8. So there's an input and an output. Let's try the 1. What happens when I plug in the 1? 1 minus 6, negative 5. Yeah, plus 8 is 3. Agreed. Hey, it's late in the afternoon. Sometimes the whole evaluation thing, it can mess with you. What about f of 2? 4 minus 12. 4 minus 12. Plugging in a 2, right? Well, it should be a 2 because negative 2 is not in our domain.
Yeah, 2.
So if you plug in a 2, you get 4 minus 12. Plus 8 is 0. And then finally, f of 3 would be, what is it? Negative 1, thank you. So unfortunately, Zoe, we tried the 0, 1, 2, 3, and we didn't come up with an output of 5 anywhere. If we had, that would have been cool, but we still would have not really used the IVT. But your suggestion of plugging in some x values on the interval was actually a pretty good one. Anna, I don't know where you were necessarily going. Could you use that data to help us?
Yeah, I was going to say that since you plug in 0 and get 8, and that's higher than 5, that you must go through 5.
Okay, so I think you're half right. I think you're getting really, really close. So she said when you plug in, you're referring to this one, right? Am I right? When you plug in a 0, you got out an 8?
Yeah.
Okay, so I like this. I think this is a good idea. How does the 8 relate to our target value of 5? Bigger, yeah. So you could say f of 0 equals 8, which is bigger than 5. Now, that by itself doesn't really prove anything other than the fact that there are going to be some y values above 5. There's one of them right there. We're going to need at least one more piece of information to get us to a place where we can prove that there is really a y value of 5. Bailey, your hand's been up for a while. What do you think?
Yeah, I was just going to say we leave one that's below 5 and above.
There you go. So if you have a y value above and then another one below, whatever our target is, doesn't that put the 5 in the middle? This is called the intermediate value theorem. Do you guys know what the word intermediate means? In the middle. Like the intermediate grades for like grade school children are like 6th, 7th grade, right? Those are intermediate grades, 5th, 6th, 7th grade, because they're right in the middle. You guys are not intermediate students, right? You're more of like the upper school students. Intermediate's in the middle. So if I were to say f of 0 equals 8, which is bigger than 5, and maybe something like f of 1 equals 3, which is less than 5, well, now we've got a number above and below. If we looked at this on a graph, I would say this could be kind of handy. I would say I've got 0 and 3. I know that, it's the other way around. F of 0 is 8. F of 1 was 3. So there's 8. There's 3. Something like that. And remember, our target value is 5. So as long as f is continuous, do you see how it would be impossible to go from here to here without hitting a y value of 5 somewhere? Mm-hmm. Right? So what we've done is we found a y value above our target. We found a y value below our target. Therefore, we kind of have this. We just need to conclude, don't we? So check it out. Here would be an example of a conclusion. Please read carefully. Watch carefully. So what if I said something along the lines of, because f of 0 is bigger than 5 and f of 1 is less than 5, f must have a y value of 5 at least once on the interval 0 to 3. What do you guys think? Is that a good? Have I concluded correctly? Have I said everything I need to say?
You do 0 to 1.
Well, so 0 to 1 is a subset of 0 to 3. And the idea was, the question said, is there going to be a y value of 5 at least once on 0 to 3? So I want to address the question. And, if you wanted to say, hey, therefore f will have a y value of 5 at least once on 0 to 1. And since 0 to 1 is a subset of 0 to 3, therefore I'm okay if you skip over that. I think that's fine. You guys all okay with this? Or Bailey, what do you think?
Do you need to write that f of x is continuous?
I have to. That's what's missing, right? So all of this reasoning over here is really neat and everything. And I'm sure you're looking at that and saying, hey, yeah, that looks like pretty good wording. But if f is not continuous, it's meaningless. It's totally meaningless. We could just skip right over 5 by having some piecewise jump or something, and it wouldn't be valid at all. So we'd have to say something like, I'll just tag it on the front. I'll say something like, because f is continuous, and we know that because it's a polynomial, and then I think we finish from there. I think we're good. So because f is continuous, and we found a value above 5, and we found another y value below 5, then f has to have a y value exactly 5, at least once. Marguerite.
Would you have to say it's a polynomial?
Yeah, right. So I don't think you should have to say that. I think I trust you enough to be like, you recognize that that's a polynomial, but you do have to say continuous. Like if you were to say, hey, f is a polynomial, therefore f is continuous, obviously there's no way that I would take off for that, but I feel like I don't really need to require that because at this point I think you probably know what a polynomial is.
Okay.
So do you see how we use the IVT here? Later on, there's a little piece in your notes that says the IVT is what we call an existence theorem. And sometimes this is frustrating because in math, aren't you guys always used to finding the answer? All the IVT really does is tell you that there is an answer, right? Did it tell you the x value where y is 5? Nope, it's just saying, right, it's like you want to know, and that would be where exactly? I don't know, it's somewhere between 0 and 3. It's just guaranteeing the existence of an answer. All of the theorems that we look at this year, like the IVT, will depend on continuity. So anyway, there you go. Let's see here. Let's take a look ahead. I know there's a couple of other good IVT questions for us. Yes. So in A, you guys got a nice rule, right? It was like x squared minus 6x plus whatever it was. Here, instead of getting a rule or an actual expression for a function, you're getting a table. These tables are really common. So this says f of x is a polynomial function. Pretty important. You might want to put therefore continuous or something just to remind yourself. And selected values of f of x are stated. Sorry about the typo. There we go. Below, what is the minimum number of times that f of x must equal 2? We've got to give some reasoning to justify ourselves, like write a sentence or two to justify it. And I would like for you guys to try this. Ready, set, go. Yes, I know. Challenging. Is this tough? Basically, you are forced to use the IVT here. There's really no way around that. Just the nature of the question is what it is. You don't really have a function that you could work with. And by the way, I don't know if anybody was tempted to do this, but if you were tempted to take these points and do some kind of like regression, did you do any regression analysis, like where you figure out what the function would be? So if you're ever tempted to do that in this class, don't. It means you're doing something wrong. So like if you have a table, like a table of data like this, the idea is just to simply use the data in the table. Don't try to come up with some curvy function that would, by regression. Don't do that. Okay, so our goal, our target here is to find the minimum number of times where f of x is equal to 2. So kind of like before, I want to use the IVT, and I'm going to basically try to find where is f of x below our target of 2 and where is it above. So I'm looking through my f of x values, my y values here, and I see right away the very first one I come to is less than my target, right? So I'll put that over here or down here and say something like f of 2 equals 0, which is less than 2. So I've established that there is certainly a value below 2. Then the very next number that I come to on my outputs is actually bigger than 2, isn't it? Okay, so that's helpful. I'm going to say f of 4 equals 3, which is bigger than 2. So isn't that one place right there, somewhere between x equals 2 and x equals 4, somewhere in there? Didn't we hit a y value of 2? We know that that's true because this is a polynomial function. It's continuous. We'll work that in here in a second. Then I go over here to 8, and 8 is still above our target value, so we can't prove that anything really happened there in regards to y equals 2. But then I get over here, and that output is now below 2 again, isn't it? So I just went from being above 2 to below 2. I'll say f of 9 equals 1, which is less than 2. So didn't the graph have to hit the y value of 2 again? Make sense? We could graph this out, I suppose, if you wanted to. And then this is below 2. So that's not going to provide another opportunity for the y values to hit 2. But then, as you see, we hit the 7, or you could even look at the 10. That's another place where the y values go above 2 again. So maybe something like f of 13 equals 7, which is bigger than 2. So that would be another place where we went from either below 2 to above 2 or vice versa. So did you guys come up with 3 times? Yes. Okay, so what is the minimum number of times? So I would say something like f of x is equal to 2 at least 3 times. And then here's my explanation, here's my justifying. Because f of x is continuous, and then I'm just going to more or less repeat myself. I'm going to say that f of 2 is less than 2, f of 4 is bigger than 2, f of 9 is less than 2, and f of 13 is bigger than 2. So every time we go from above to below or below to above, we've got to hit 2 somewhere in there. Again, we're not finding an answer. We're finding out that there are answers, right? That the answers actually exist. Make sense? Okay. Any questions? Anna.
So if, just this is not like how to write it out, so like, would you want us to write in the explanation that like f of 2 is less than 2 versus that, or could you have just said that there are 3 times like when the y values pass through numbers below the y value of 2 to numbers that are above the y value of 2? And then
If you had this to go along with that, yes. So one of the requirements that I will have, and I got to be honest with you, I'm just trying to train you guys for like the AP test later on. So one of their requirements is that you have clearly demonstrated that you use data from the table. So if all you said is, hey, there's some y values above and some y values below, they could justifiably say, well, where'd you get that from? So they want to see, and I want to see, that you've actually pulled data from the table. And it doesn't have to be written just like that. Like honestly, if you took this that I'm about to highlight in red, if you took this and you just said because and like drew an arrow over there or something, I'm fine with that. I'm going to try to tie it up neatly and make it sound as good as I can make it sound. But if you just said, you know, basically the unhighlighted part, and then you said, and also look at all these points that I pulled out of the table, I think I'd be fine with that. Great question. Yeah, Bailey.
Why didn't you use the f of 7 and the f of 12?
So I could have. I certainly could have. But I got all the information I really needed with these other numbers. So like if I wanted to, instead of this, if I wanted to write f of 7 equals 8, which is bigger than 2, I certainly could have done that. I wouldn't need to because I already had this. I've already established that I've gone from below 2 to above 2. And honestly, like if you're potentially wasting time. You don't need to repeat yourself. So let me put it like this. So this was below 2, this was above, and this was also above. So I really only needed to use one of the 2 aboves.
Okay.
I could use either of them. There's really no need to use both of them because all I'm trying to do is prove that y equaled 2 somewhere in there. And if I was above and then stayed above, then didn't really help. But as soon as you go back down below, which was right there, well, now we just picked up another time. Yeah. Okay, anybody else with a question? Or these are really great questions. I really appreciate it. Sometimes I can predict what you'll ask, and other times I have no idea. So I appreciate you asking. Anybody else? Okay, cool. Let's keep going. So I've got, I think, 2 more good ones here. 2 more real good ones. Yes, I do. Okay. So take a look at C, very conceptual here. Are you guys okay with the term x-intercepts? It's where the graph touches or crosses the x-axis. Okay, cool. All right, so take a look at C. It says 3 values of g of x are shown below. What is the minimum number of x-intercepts for g of x? Explain your reasoning. So take a minute, write it down, think it over, discuss amongst yourselves. Don't ask me any questions yet, because you asking me questions might unlock something I don't want to be unlocked yet for everybody else. So discuss amongst yourselves. That's fine. But give it a shot. What do you guys think? What is the minimum number of x-intercepts? 1? None? So far I've heard 1, none, and?
Cannot be determined because
Can
we
it-
don't know if it's
continuous.
cannot be determined because we don't know if it's continuous or not. Oh, the light bulb just came on. I love it. So that was the thing. I didn't know if, Marguerite, if you were going to ask about continuity. Notice nowhere it tells you what type of function this is or doesn't say anything about continuity. And so really, truly, Marguerite, you were on the right track there. Not enough info. You need to know about continuity. Like if I told you that G was a continuous function, then what would the answer be? It would be 1, minimum of 1. But because we don't know about continuity, we've got to say not enough info. We need to know about continuity. So as it stands, we just don't know. So what's the point of that? To kind of reinforce to you guys again, the condition for the IVT, continuity. Nice job. Well done. Okay, so then our final example for the day, I think this will tie things up pretty nicely for us, is D. So it gives you a piecewise function here, piecewise graph. And it says f of x equals that graph right there. Use the IVT to show that f of x equals 5.217 at least once on the interval -3 to 3. Remember to confirm the IVT's condition before you use the IVT. So I would say, surprisingly enough, I think that this can definitely be done without a calculator. And I would encourage you to do so. Okay? But before you do anything with the IVT or plugging anything in, we need to confirm the condition. And what is the condition? Continuity. That's right, Maddie. So the condition being continuity. Do you guys remember from, I want to say, it would be 1 class ago, I think. Remember the little statement about continuity? Limit from the left must equal limit from the right, must equal the value of the function at that point. I need you guys to use that to confirm that, yes, this truly is continuous. Or maybe you find out that this is not continuous, and we just stop and say IVT doesn't apply. Because that can happen too. It would be, but if you forget to check that, then you're like, oh, if only I would have checked that. So please confirm or deny the continuity, and then if you can confirm, then move on. Okay?
I'm pretty sure you did.
So if you guys are just wrapping things up, just like lend me like one ear and you keep working. We'll just kind of try to blend this together and get finished up well. So like I said before, the condition is continuity, so we need to confirm that or perhaps deny that. So here's how you do that. We're going to say limit as x approaches 1 from the left, and this would be the polynomial piece. Has to equal the limit as x approaches 1 from the right. This would be the cosine of pi x piece of the piecewise, and those both have to equal f of 1. So if you are asked to confirm continuity, deny continuity, prove continuity, basically whatever it is, something to do with continuity, you need to start off with a statement like that. Limit from the left, perhaps equals limit from the right, equals the value of the function at that point. You guys hear? Hey, listen. How many times do you hear teachers say, always do this? Rarely, right? Because that's a very broad brush to paint with, right? Always do this. So I'm telling you, if you're ever asked to confirm or deny or do something with continuity, always start with that.
Okay.
Question. Go ahead.
If, could you like just write like limit of f of x is x approaches 1 from the right is equal to limit of f of x and s approaches 1 from the left, and just like prove or disprove that instead of writing like out what
Yeah, so in other words,
like the actual piecewise.
in other words, just put f of x here and f of x there.
Yeah.
I think I'm okay with it.
Say equals f of x, or could I just prove that it's the function doesn't? Or that
No, say that last thing again.
Like, do I need to put equals f of
1?
1?
Yes.
Okay.
Yep, you definitely have to do that. Because if you don't put that, all you're proving is that the behavior from the left and the right is the same, which proves that the limit exists, but it doesn't prove continuity. Because you could have...
But if you prove that the limit doesn't exist, doesn't that prove that it's not?
Yeah, if you prove that the limit doesn't exist, then you could just stop right there.
Okay, then that's what I...
Okay. But if it really is continuous, then you do have to include the f of 1.
Okay, so might as well just write.
Might as well.
Wait, what did you do? You plug 1 into that?
Well, yeah, so I haven't evaluated them yet. Does that make sense?
Yeah.
So, yeah, Audrey, go ahead.
So this is kind of
Shh, quiet down, please.
so if like
cosine of pi over x is less than 5.217, and then
Can we not go there yet?
Okay.
We'll get there. We will. So let's evaluate these limits. If you evaluate the limits, you get here, you can do this by direct substitution, right? It works out pretty nicely. So 1 minus 2 is negative 1. And cosine of pi, according to the unit circle, is negative 1. And of course, f of 1 is contained within the parabola, also negative 1. Look at that. F of x is continuous, right? Okay, so I can put f of x is continuous, therefore the IVT applies. You could do something like that. But now we need to use the IVT. And remember what the IVT, I'm sorry, Marguerite, go ahead.
Wait, sorry, I was paying attention. For the f of 1,
Yep.
how'd you get negative 1?
So f of 1 is contained within this piece right here because of the or equal to. So this piece, x squared minus 2, determines the graph for x being less than 1 or equal to 1, right? So to find out what f of 1 is, you would use the polynomial piece. So that kind of takes care of 2 of these steps. Okay, guys, to wrap this up, for the IVT, you have to find a value above our target and a value below our target. And our interval is -3 to 3. Did you guys plug some numbers in and get some outputs? What'd you plug in, Audrey?
Well, I plugged in -3 for both of them, and then I got -1.
Well, hold on, guys. Hey, cut it. There's still time. Let's finish well. Now, you just said I plugged in -3 for both of them. There's a problem with that. -3 is valid for the parabola, but -3 is most definitely not valid for the cosine of pi x, right?
Yeah.
Only numbers that are bigger than 1. So we could plug in -3. If I plug in -3, this would be -3 squared minus 2. So that would be 7, right?
Yeah.
So that's bigger than 5.217. So then what other number could we plug in? There's a bunch of them. Say again? Plug in 3? Okay. So f of 3 would equal cosine of 3 pi.
Yes.
And what is cosine of 3 pi? -1. Yeah, unit circle stuff. So that's -1. And how does that relate to our target?
It's less than.
It's less than. Look at that. So we just used the IVT, or we're in the process of using the IVT. We just found a number that is above our target and a number that is below our target. And you could have plugged in other numbers, but the -3 and the 3, those work pretty well. So what I can say then is, because f of x is continuous and f of -3, is bigger than the target, and f of +3 is less than the target of 5.217, f of x must equal 5.217 at least once. Sorry, I'm running into the board there. On the interval from -3 to 3. We basically did, 3 or 4 IVT questions. Are you getting the sense of just find a number above the target, number below the target, and as long as the function is continuous, we got it? Okay, that's fantastic, and that was almost perfect timing. You guys have a wonderful afternoon. See you, no, not tomorrow, Wednesday, right? Wednesday, okay. All right, cool. Have a great rest of your day. Audrey, what was your question?